October 1924. The room was filled with smoke and skepticism. Standing before a group of doubtful journalists was a man whose invention was being called suicide gas. This was Thomas Midgley Jr., a brilliant chemist working for General Motors. To prove the safety of his new fuel, he did the unthinkable. First, he demonstratively washed his hands in tetraethyllead. Then he brought a flask to his face and inhaled the poisonous fumes deeply for precisely 60 seconds. The room erupted in shock, then applause. The world believed him. But it was the most cynical bluff in the history of science. Behind this bravado lay a year of agonizing treatment for severe lead poisoning. Midgley knew it was poison. He himself had become its first victim. What compelled a man to commit such a deadly deception? His actions initiated the first catastrophe. Bone analysis reveals that the skeleton of a modern human contains 1,000 times more lead than that of people who lived before Midgley. How did a substance that saved the automotive industry become a global poison that has touched every one of us? This is the first question, but there was a second catastrophe. How did the same man, while creating an absolute miracle substance for safe refrigerators, fail to notice for decades that it was literally tearing apart the planet's protective ozone layer? This is a story of how a brilliant solution to one problem spawned two global threats. We will answer both these questions and reveal the mechanism by which good intentions, combined with corporate greed, lead to irreversible consequences. It all began with a simple sound, a metallic knocking in the engine. Today we consider it a sign of malfunction, but in the early 20th century it was the chief adversary of engineers and a fundamental barrier preventing General Motors from winning the war against Ford. This knocking, or detonation, was more than just a sound. It was uncontrolled micro-explosions of fuel in the cylinder. Instead of a single smooth thrust propelling the piston, the fuel exploded chaotically, like water creating a water hammer in a pipe. These explosions destroyed engines and prevented an increase in power. While Ford was producing millions of inexpensive but weak cars, GM's entire business model, built on powerful vehicles, was on the verge of collapse. This was no longer just a technical issue, but an economic problem worth billions of dollars. To solve it, research head Charles Kettering deployed his most ambitious engineer, Thomas Midgley. This assignment gave him carte blanche for the wildest experiments. And they began with an absurd idea. How could a brilliant chemist believe that the color of fuel influenced a complex physical process? Desperation. The very first experiments, adding iodine to gasoline, yielded results, knocking decreased, and the fuel turned a reddish color. Thus, a beautiful but false theory was born. Perhaps the red light spectrum somehow stabilized combustion. In a burst of enthusiasm, Midgley even added anemone juice to the fuel, hoping for its red pigment. But reality struck. Hundreds of other red dyes had no effect. Months of fruitless searching and increasing pressure from management shattered the illusion. It was then that Midgley realized it wasn't about the color of iodine, but its chemical properties, its place in the periodic table. The focus shifted from alchemy to science, and this systematic search would lead him to an element known for its toxicity since the Roman Empire. Midgley's lab transformed into an assembly line for testing elements from the periodic table. They tried selenium, tellurium, aniline. Some worked but were too expensive or inefficient. The search was methodical, almost routine, until December 9, 1921, when they tested tetraethyllead. The effect was astonishing. Just 1 gram of this substance per gallon of fuel completely eliminated knocking. It was the magic bullet they had been searching for 7 years. A scientific triumph. But there was another, ominous figure. The toxicity of lead had been known to humanity for over 2,000 years. Midgley and his team could not have been unaware that they held in their hands a potent neurotoxin, destructive to the nervous system. They had created the ideal fuel, but at what cost? The euphoria at General Motors was short-lived. The problem was solved, the patent secured, the path to market dominance open. Thomas Midgley became a corporate hero. But then reality struck hard. At the very first factories of DuPont and Standard Oil, which produced the new additive, workers began to go insane en masse. They suffered from hallucinations, severe psychoses, and convulsions. Many threw themselves out of windows. Newspapers dubbed the new product loony gas. In the first 2 years alone, 15 deaths and over 300 cases of severe poisoning were recorded. At this point, the corporation and Midgley himself faced a choice: halt production and admit the deadly danger, or go to any lengths to conceal the truth. Their reaction initiated the mechanism of the most cynical deception in technological history. To save the reputation of the deadly product, the corporation leveraged its greatest asset, the inventor himself. But what compelled Thomas Midgley, who had just spent a year recovering from lead poisoning, to personally demonstrate the safety of this poison? The answer: cynicism. At the famous press conference, confident and charismatic, he washed his hands in tetraethyllead. Then he deeply inhaled its fumes, smilingly declaring he could do it every day. To the public, this was irrefutable proof. But behind the scenes, he concealed an official diagnosis and doctor's orders to stay away from lead compounds. It was not a scientific experiment, but a spectacle dictated by pressure from General Motors. And it worked. The press was convinced, and sales of leaded gasoline soared. The price of this show was not measured in applause, but in lives. But one show was not enough. Corporations needed a systemic mechanism of deception, and they created one. How did they manage not just to suppress the scandal of deaths, but to turn a poison into a symbol of progress? They attacked on two fronts: scientific and psychological. First, General Motors and DuPont created a joint venture, the Ethyl Corporation. It began funding research at universities, hiring loyal scientists, and publishing reports proving the product's relative safety. This created an illusion of scientific consensus. Second, they employed a master trick: manipulating language. The word lead was completely removed from all promotional materials. It was replaced with the trademark ethyl. The poison was simply renamed. This manipulation worked like a sieve. The corporation filtered facts, leaving convenient words like ethyl and efficiency. And the word lead and data on deaths were filtered out. Have you ever bought a product trusting a pretty name? This mechanism still works today. You're under pressure from one of the world's largest corporations. Your career, fame, and vast sums of money are at stake. What would you choose, an inconvenient truth or resounding success? Midgley faced precisely this choice. One might assume that, as a chemist rather than a toxicologist, he himself wanted to believe that the danger only applied to production. But the facts suggest otherwise. He didn't just read reports, he himself was ill. He saw deaths. He knew exactly what he was dealing with. This was not ignorance, it was a conscious moral choice, to side with the corporation against society. This is the tragedy of an inventor who could not abandon his creation, even when he learned it was a killer. His personal pride and ambition became the final component in this toxic mixture, and responsibility for this choice would catch up with him years later in the most ironic way. The PR campaign succeeded. The product was on the market, and the world was convinced of its safety. What next? A visible triumph. Leaded gasoline conquered the world. Cars became more powerful, faster, and more accessible. Aviation gained fuel for more potent engines. General Motors and DuPont reaped astronomical profits. But behind every exhaust plume lurked an invisible threat. Microparticles of lead did not disappear. They settled on the soil, entered the water, fields, and food chains. By the 1970s, in the U.S. alone, over 200,000 tons of lead were released into the atmosphere annually. Billions of cars worldwide, year after year, spewed tons of neurotoxin into the air. While on the surface the world grew faster and louder, in silence, at a micro level, the planet began to slowly cover itself with a thin layer of poison. But how to measure this poison, if by the mid-20th century it was absolutely everywhere? This paradox would have stopped anyone, but not geochemist Clair Patterson. His goal was monumental: to determine the age of the Earth by analyzing lead isotopes in ancient meteorites. The work demanded perfect purity. But every one of his samples turned out to be contaminated with lead from the air. Obsessed with finding a pure sample, he created the first ultra-clean room in history, sterilizing everything around him. And there, in absolute silence, he realized the problem wasn't in his laboratory. The problem was that the entire world was poisoned. His analysis proved the isotopic composition of this excess lead was identical to that produced by the Ethyl Corporation. A scientist seeking the planet's age accidentally found evidence of a crime against it. This discovery prompted a personal question: how much had the chemical composition of our own bodies changed? To peer into a pristine past, Patterson and other scientists analyzed layers of ancient Greenland ice and the bones of people who lived before Midgley, for example, from 1600-year-old Peruvian burials. The result was astonishing. Modern human bones contain 700 and sometimes even 1,200 times more lead than those of our ancestors. This was not just an elevated level. It was a fundamental change in the chemistry of our species. For children, this neurotoxin became a silent epidemic, causing a decline in average IQ and an increase in behavioral problems across entire generations. Lead in our bones turned into a ticking time bomb. Under stress, it is released back into the bloodstream, poisoning the body decades later. A multi-billion-dollar industry could not ignore such evidence. Its response was brutal. Ethyl Corporation and oil companies launched a war against the lone scientist. They revoked his research grants. They pressured his institute's leadership, demanding his dismissal. They funded articles discrediting his methods. But Patterson did not break. He transformed his scientific work into a crusade, testifying before Congress and proving the truth. His struggle lasted almost 20 years, but it was successful. His data formed the basis of the 1970 Clean Air Act, which initiated the ban on leaded gasoline worldwide. But while one man was correcting the consequences of a disaster, its creator was already preparing a second one. By 1930, Thomas Midgley was no longer just an engineer, but the vice president of Ethyl Corporation. Famous and respected, he received a new assignment from a General Motors subsidiary. And the task was noble: to make household refrigerators safe. At the time, they were death traps. They used poisonous ammonia or sulfur dioxide as refrigerants. A refrigerator was like a human body whose veins were filled with poison. The slightest leak, and an entire family could die in their sleep. The world urgently needed a new, absolutely safe gas. And Midgley, a genius at solving insoluble problems, enthusiastically took on the task. How could a common kitchen appliance kill an entire family in their sleep? The veins of early refrigerators were filled with poisonous ammonia or corrosive sulfur dioxide. A microscopic leak would turn a kitchen into a gas chamber. In 1929, over 100 people died in a Cleveland hospital due to such a leak. The industry needed a substance that was simultaneously non-toxic, non-flammable, and stable, an impossible task. But instead of years of searching, as with lead, Midgley found a solution in just 3 days. He didn't sift through thousands of compounds. He took the periodic table and used it as a sieve, filtering out dangerous elements. The circle narrowed to a few candidates, but all reference books stated fluorine compounds are extremely toxic. A less confident scientist would have stopped. But Midgley hypothesized that in a stable bond with carbon, fluorine would be safe. He commissioned the synthesis of dichloro-difluoromethane, the world's first chlorofluorocarbon, or Freon. To prove its safety, Midgley staged another show. At the 1930 American Chemical Society convention, he took the stage. Silence filled the hall. He brought a flask of the new gas to his face and took a deep theatrical breath, filling his lungs with it. Then he slowly exhaled onto a burning candle. The flame extinguished. The hall erupted in applause. It was an absolute triumph. The world had received a miracle gas, a symbol of victory over nature's imperfections. But in the euphoria, no one asked the crucial question: where does a gas so inert that it doesn't even react in human lungs disappear to? It was this very property, its incredible stability, that transformed a savior into an invisible killer of planetary scale. The world had received a perfect, absolutely safe gas. What could possibly go wrong this time? Freon began its triumphant march across the planet. It was everywhere, in refrigerators, air conditioners, deodorants, hairsprays. Production grew exponentially, but its main virtue, chemical stability, turned out to be a curse. Upon entering the atmosphere, the gas did not break down. It did not dissolve in rain. Billions of tons of this invisible gas began its slow, multi-year ascent. Higher and higher, through all layers of the atmosphere, to the very edge of the sky. There, it awaited the only catalyst capable of unleashing the hidden destroyer, the sun's harsh ultraviolet radiation. A single chlorine atom, knocked out of a Freon molecule, triggers a chain reaction capable of destroying up to 100,000 ozone molecules. But the world would only learn of this 40 years later. How could a gas that a person inhales without harm become a threat to the entire planet? This was the peak of the illusion. Absolute safety down here concealed a mechanism of total destruction up there. The ozone layer is the planet's cosmic sunscreen. For billions of years, it has protected life from harsh ultraviolet radiation. And a Freon molecule in the lower atmosphere was a chemical ideal, inert, stable, reacting with nothing. It seemed that if the gas was safe here, it was safe everywhere. But the picture changes when a Freon molecule drifts upward for decades. There in the stratosphere, under bombardment from the very ultraviolet light that ozone protects us from, its superstable structure breaks down. Its Achilles heel is released, a single chlorine atom. This atom is not just -1 ozone molecule. It acts as an invulnerable catalyst, like a chemical wolf that single-handedly destroys a flock of 100,000 sheep before being stopped. And this theoretical model did not remain just numbers on paper for long. Who first sounded the alarm while the world was enchanted by the miracle gas? Not environmentalists or doctors, but two scientists, Sherwood Rowland and Mario Molina, who in 1973 asked a simple academic question: where do all these freons eventually go? It was routine research, driven by scientific curiosity. They had no intention of exposing anything. They simply followed the data, tracking the life cycle of a chemically boring molecule. The reality revealed by their calculations was devastating. They realized they had stumbled upon a mechanism of planetary suicide. Rowland famously told his wife, "The work is going very well, but it looks like the end of the world." Their findings were met with ridicule. The chemical industry called the theory science fiction, and the scientists alarmists, and even KGB agents. This furious attack was an exact replica of the tactics used against Clair Patterson. And it meant only one thing: the theory was correct. How did abstract calculations turn into a fact that shook the world? The answer came from the coldest continent, Antarctica. And, at first, it was mistaken for equipment malfunction. For years, British scientists at Halley Bay routinely measured the ozone layer. In the early 80s, their instruments began showing anomalously low values. The initial reaction was error. They ordered new equipment, convinced that such readings could not exist in nature. In 1985, they realized the instruments were not lying. An article published in Nature first introduced the term ozone hole. This was not a predicted 10% depletion, but a catastrophic plunge of 30%, and in some places 40%. Reality proved scarier than the worst forecasts. But visualization changed everything. When NASA satellite data showed this hole as a massive purple patch over Antarctica, the invisible threat became visible. It worked like a drop of ink in a glass of water. Abstract chemistry transformed into a concrete, frightening map that compelled humanity to do something unprecedented. Humanity faced its first human-made global threat, proven and visible. What was our response? Panic, denial, or collective action? This became a test of maturity for all civilization. The response was a triumph. In 1987, the Montreal Protocol was signed. For the first time in history, almost all countries in the world agreed to ban the production of an entire class of chemical substances. It was a moment of rare global unity when humanity acted as a single organism. However, behind the scenes of this victory, the struggle continued. Corporations, including DuPont, did not give up. They lobbied for delays, questioned the science, and promoted transitional refrigerants that were also harmful, albeit to a lesser extent. This was an attempt to maintain market share at all costs. The ozone layer is slowly recovering today, proving that collective action works. Forecasts predict it will return to 1980 levels by approximately 2066. But we were on the brink of disaster. And this closeness to the edge is a direct legacy of Thomas Midgley's second miracle invention. What do a geochemist obsessed with measuring the Earth's age and two chemists studying molecular behavior in the atmosphere have in common? At first glance, nothing. But it was Clair Patterson, Sherwood Rowland, and Mario Molina who became the main adversaries of the most powerful corporations of their time. They were not activists. Patterson, in his sterile laboratory, boiled instruments in acid, trying to find a pure sample for fundamental science. Rowland and Molina were solving a purely academic problem. But it was precisely their detachment that allowed them to see the truth. They were not part of the industry, and they lacked its blind spots. When they realized the scale of the threat, science ceased to be a job. It became a moral duty. And this integrity turned them into targets for a ruthless machine of truth suppression. How do multi-billion-dollar industries fight against a single scientist armed only with facts? Following a well-rehearsed three-step scenario. Step 1. Denial and delay. Corporations claim the data is preliminary and more research is needed. The goal is not to disprove but to buy time, continuing to make profits. But when that's not enough, Step 2 comes into play. Personal attack. The focus shifts from the data to the scientist. They are accused of seeking fame and bias. The goal is to destroy trust in the source. And the final, most insidious step, the factory of doubt. Corporations fund their own independent studies that publish contradictory results. Their goal is not to prove themselves right, but to create an illusion of scientific dispute among the public and politicians, to paralyze decision-making for years. A familiar scenario, isn't it? What personal price did these individuals pay? Clair Patterson was stripped of contracts with the American Petroleum Institute and the Atomic Energy Commission, cutting him off from funding. Rowland and Molina were no longer invited to conferences, and colleagues avoided them. The system tried to isolate them, but it underestimated their persistence. Patterson found other funding sources and continued his work. Rowland and Molina began speaking to the general public, explaining the threat directly. And they won. Patterson's data formed the basis of the 1970 Clean Air Act, which initiated the ban on leaded gasoline. And in 1995, Rowland and Molina received the Nobel Prize in Chemistry for work that had been called science fiction for 20 years. But while they waged their long battles, the creator of both problems was approaching his own very personal end. We have seen two catastrophes and the heroes who fought them. But where was Thomas Midgley himself in all this drama? He died in 1944, 20 years before Patterson's work and 30 years before Rowland's theory. He never learned about the hole in the ozone layer or the planet's widespread lead poisoning. He passed away absolutely convinced that he was one of humanity's greatest benefactors. His obituaries praised him as the man who made cars powerful and refrigerators safe. But his death conceals the final, most cruel and symbolic irony of this entire story. And to understand it, we need to move from the global scale to a single room where the brilliant inventor worked on his last creation. In 1940, at the peak of his career, 51-year-old Thomas Midgley contracted polio. The disease left him with paralyzed legs and almost no strength in his arms. The man whose mind drove industry found himself confined to bed, completely helpless. But paralysis chained his body, not his mind. Lying in bed, Midgley saw not a tragedy, but another engineering challenge. How could he, paralyzed, sit up and stand on his own? He approached his illness just as he had approached engine knocking, as a technical problem requiring an elegant solution. And he set about creating his last, most personal invention. In his bedroom, he constructed a complex system of ropes, motorized pulleys, and carefully calculated counterweights. It was his personal exoskeleton. By pressing switches, he could lift his torso, sit up, and transfer to a chair. It was a triumph of engineering over physical infirmity, his final masterpiece, proving that his genius was still alive. But, as with tetraethyllead and Freons, this invention solved one problem while creating another, hidden and deadly. In this intricate web of ropes, as in his chemical formulas, lay an unforeseen, fatal vulnerability. On November 2, 1944, in the quiet of his bedroom, he used his device as usual. And in an instant, the system that granted him freedom became a death trap, one of the bad. Ropes accidentally wrapped around his neck. The mechanism created to lift him began to strangle him. His weakened body could not fight back. According to the coroner's report, the cause of death was asphyxiation due to strangulation by the straps of his own lifting device. Thomas Midgley Jr. was killed by his last invention. But this death is not just a tragic incident, it is a perfect, chilling symbol of his entire legacy. An inventor killed by his own creation. Is this a cruel twist of fate or something more? It is the perfect metaphor for his entire life. He created brilliant solutions for specific problems, being absolutely blind to the side effects, which proved to be far more destructive. But this metaphor extends beyond the life of one man. It is a metaphor for our entire technological society. We have created incredibly complex systems to make life better. But now we risk getting entangled in their consequences ourselves: climate change, planetary pollution, resource depletion. The story of Thomas Midgley is a warning. And now, knowing it to the end, we must ask the main question: what does his legacy teach us? The first lesson of his legacy is about the price of progress. It takes us back to engine knocking and the brilliant solution, tetraethyllead. We remember how deaths at DuPont factories forced corporations and Midgley himself to resort to deception. They renamed the poison to the harmless ethyl, and for decades turned a blind eye to scientific data about its harm, all for colossal profits. This lesson proves ignoring a minor side effect leads to a planetary catastrophe, and Clair Patterson found the evidence of this: crime in our own bones. The lead content in the skeleton of a modern human is 700, and sometimes even 1,200 times higher than the norm. This is the largest mass poisoning in human history, spanning half a century and affecting the health of hundreds of millions of people, especially children. The second lesson is about the ticking time bomb disguised as perfect safety. It begins with a noble goal: to save families from poisonous refrigerators. And then, triumph, Freon, non-toxic, non-flammable, an absolutely inert miracle gas. Midgley inhaled it on stage, demonstrating its harmlessness. But it was this perfect property, its incredible stability, that turned it into a weapon. Freon molecules took 10 to 20 years to slowly rise into the stratosphere. There, high above, they initiated a chain reaction of ozone destruction. This lesson teaches that the greatest danger may lie not in what technology does immediately, but in what it doesn't do for decades, silently accumulating its destructive potential. So who was Thomas Midgley, a villain or a genius? A simple answer is impossible. On the one hand, he consciously concealed his lead poisoning and promoted a deadly product. On the other hand, he sincerely solved real problems of his time. The key to his personality is blind techno-optimism. Midgley believed that any problem could be solved through engineering, and any side effects eliminated by new inventions. His approach was akin to a carpenter who only has a hammer. To him, every problem looked like a nail. He didn't ask if a wall was needed. He simply looked for the most effective way to drive the nail. Tragedy is the tragedy of brilliance devoid of wisdom and an ethical compass. His story is an eternal warning that the ability to invent does not grant the right to implement. Ultimately, we have two main culprits. We have seen a brilliant inventor who created two monsters, and we have seen corporations that release them into the world, hiding the truth for profit. So who bears primary responsibility for the two largest environmental catastrophes of the 20th century? On one side, the inventor, the man whose genius spawned the threat. On the other, the corporations, the system that turned the threat into a global catastrophe. This is an eternal debate about personal versus systemic responsibility. Please write a single word in the comments that reflects your opinion: inventor or corporations. No explanations, just your verdict. Let's see whose responsibility, in your opinion, was decisive.